Welcome everybody to another video lesson. Today we're going to wrap up our Unit 8 concepts with cross products in space. All right, so we're going to find the cross products of vectors, and then we're going to use those cross products to find some areas and some volumes of specific shapes. So let's hop right into our concepts. Okay, what is a cross product? Well, up until now, we've been looking at the dot product, right? And the dot product has given us some scalar value, some scalar quantity. Now, when we take our cross products, we're actually going to get a vector quantity. And that vector quantity is going to be perpendicular to the plane that is containing A and B. So if I have these vectors A and B here, we can see that there is a plane that contains these two vectors, right? And now if I take the cross product, we call it A cross B. So if I take A cross B, that's going to yield this perpendicular vector to this plane that contains A and B. So that is what we're doing here when we find the cross product of two vectors. Now there is a formula for our cross product. It is quite long, and there's a lot of A's, B's, 1, 2's, and 3's. So I would recommend you not just memorize this formula and instead understand where the formula comes from. So when I take the cross product of A cross B, what we're doing here is, since we are in 3 dimensions, I'm going to set up a 3x3 matrix, and I'm going to take the determinant of this matrix. So now we can see the first row here is going to be all of my unit vectors I, j, and k. And then what's going to fall under them will be the components of A and B. So in the second row, I'll have the I component, the j component, and the k component for A, and then the same for B. So that's going to make up my matrix here. And then we're going to go ahead and take the determinant of this 3x3 matrix, which if you don't remember how to do, there are videos on how to do this. However, we can quickly go over it. So we'll go ahead and circle the top row, and then we're going to circle the first column. And then we're going to take a 2x2. The resulting 2x2 matrix is what is not circled right here. Okay, so I've got A2, A3, B2, B3. So we're going to take the determinant of that 2x2, which is a lot easier, and then what we're going to multiply by is this element right here, which in this case is a unit vector I. And then we can subtract. If I move over my circle to the next column, I'll have a 2x2 determinant again, so it's going to be A1, A3, B1, B3, and I'll take the determinant of that little 2x2, and we'll multiply that by what's in our crosshairs here, which is unit vector j. And then I'll go ahead and add, again, one more time. We'll do this. We'll move our column over to the third column. Now what's in the crosshairs is unit vector k, and we have the resulting 2x2. That's what we're going to take the determinant of. So I can start taking the determinants of my 2x2 matrices, and it's going to look something like this, which is the exact equation and formula that we have up here. Okay, but again, this formula is, it's kind of confusing, right? There's a lot of A's, B's, and C's, or A's and P's, 1's, 2's, and 3's. And so instead of just memorizing this, I'd recommend that you understand where this comes from and how to take the dot product of two vectors, okay? Another concept we're going to go over, and a very applicable concept for us, is going to be torque. Okay, the definition of torque is the measure of a force that can cause an object to rotate about an axis. So think about a wrench or some sort of tool tightening like a nut or a screw, right? So if I have my tool here, then this is going to be, the length of that tool will represent a radius vector r, and then the force that you apply to that tool would be your force vector, okay? And then what results is going to be, again, it's going to be perpendicular to these two vectors because it's the cross product, and that's going to be torque, okay? So our formula for torque is going to be r cross f. R cross f, where r is the radius, that's how far I'm applying the torque, okay? How far away from the object am I applying the force, rather, and then the force vector itself, all right? And our units are going to be Newton meters or kilogram meter squared per second squared. And our third concept is going to be a triple scalar product. Now this is going to be used for what is called a parallelepiped, okay? Now this is a shape that is created from 3 vectors when they share the same initial point, but they're in different planes. So you can see here we have vectors A, B, and C. And what we have here, this resulting shape, is going to be a polyhedron with faces that are all parallelograms. So you can see this kind of, it's like a cube that got slanted off to the side, right? So all these faces are parallelograms on this shape here. Okay, this is a parallelepiped. So to find the volume of a parallelepiped, that is what a triple scalar product is going to yield. Okay, and we find this by taking vector C, dotting that. Okay, so C dot A cross B. So how we do that, what that looks like, is I've got A cross B is what this looks like right here, right? And the only difference here is I'm going to take this first row, that's A, J, and K, and I am going to substitute in my components for vector C. Okay, that's all I'm doing. Now notice here that since all I have here are going to be component values, okay, there are no unit vectors, no vectors here in sight. So these are all just component values. So this is going to give me a scalar quantity. And that scalar quantity is going to be the volume of the shape that we have here, all right? So those are our three concepts. Let's go ahead and put these to practice with some examples. Okay, first example, we're going to find the cross product of U and V and show that U cross V is orthogonal to both U and V. So we've got U and V here in component form. We can go ahead and create our 3x3 matrix and just take the determinant of this matrix like so. We'll go ahead and take the determinant of our 2x2s. Don't forget our minus here. Okay, that's a minus for that second one. And we can go ahead and simplify all this, and we'll get U cross V is 9i minus 21j minus 6k. And we can put that in component form as well, just like that. Okay, so that's the first part, that's finding the cross product. Now we need to show that U cross V is orthogonal to both U and V. And we can do that by finding the dot product of U cross V with both U and V. Because if you remember, if you find the dot product of two orthogonal vectors, that dot product is always going to be 0, right? So this here is just a vector that we just found, and U is just a vector that we were given. So we can take the dot product of those two vectors, which we've done before. So we'll have 36 minus 42 plus 6, and that's going to be 0, right? So those two are orthogonal. So now we just need to do the same thing, but with vector V. Take the dot product. Again, we're given V. We found U cross V. Take the dot product. We've got 45 minus 21 minus 24. That's going to be 0. So that checks out. U cross V is orthogonal to both of our original vectors. All right, now let's take a look at some torque problems. We've got a mechanic using a wrench that's 0.4 meters long to tighten a nut. We need to find the magnitude and direction of the torque about the nut if the force is 30 newtons straight down to the end of the handle when it is 35 degrees above the positive x-axis. Okay, the positive x-axis. We need to understand that. So we've got our three-dimensional axes here. We can go ahead, our three-dimensional coordinate planes. We need to kind of write these vectors in so we can start to picture what's going on here. Okay, so we have the wrench that is 35 degrees above the x-axis. Okay, so that wrench is going to represent our radius vector r. Okay, our radius vector r. So that wrench is going to look like this, and this is in line with the x-axis, which means if I were to put this on a plane, it would be the xz plane, right? The xz plane only. There would be no y component for my vector r. Hopefully you can kind of see that. And then for our force vector of 30 newtons, it says straight down, okay? So if that is straight down, then that is in line with z, right? And if that's in line with z, then I have no y component as well. So I know right off the bat that if I were to take the dot product to find the torque of the dot product, or not the dot product, but the cross product, r cross f, I know that my torque is going to be in the y direction, okay? Or parallel to the y-axis at least. Okay, so let's take a look at the magnitudes for r and f. Okay, the magnitudes were given as 4 meters long, right? And then the force that we're applying is 30 newtons. So we're going to denote those as lowercase m and capital N for newtons. And now let's try to put our force in component form. Now, since that is only in the z-axis, right, it's parallel with the z-axis, there is no x or y coordinates for this, or no x or y components rather for this vector, okay, because it is all in the z-axis. It's straight up and down. Even though it's moved out here, it's still all up and down. It's not coming out left or right in the y or x-axis at all, okay? So now we need to find r in component form, so we can go ahead and do that by taking the magnitude of r, multiplying that by the cosine, and we're just trying to find these components here, this x component and then this z component, okay? Hopefully you can see, kind of picture this coming out towards you out from your screen, all right? So when we do that, we can input our magnitude here, and we know our angle is 35 degrees. Okay, and now we can just go and find r cross f, because r cross f is our torque. So we've got our matrix set up, and I went ahead and instead of plugging this in, I just put r1 and r3. r2 would be here, right? But that's just 0, so I just plugged in 0. And then for my f components, I have 0, 0, negative 30. So then we can go ahead and take the determinant of our matrix here, which looks like this, and we have a lot of zeros in here, which makes sense, right? Because this torque is going to be in line with my y-axis, right? Now, if that's in line with my y-axis, then really I know that my I components and my k components should drop out, which in fact they do. If I take the determinant of these, those drop out, and I'm only left with minus 0.4 cosine 35 times negative 30 times unit vector j, right? So the torque that's being applied here is approximately 9.8 Newton meters parallel to the positive y-axis, okay? If you plug that into a calculator, that's about 9.8, right? So that is how you would apply this for torque. Okay, now let's take a look at finding the area of a parallelogram. So if we have two vectors, okay, u and v, then they can, taking the cross product of those and then taking the magnitude of that cross product is going to yield the area of the resulting parallelogram, okay, from those two vectors. So here I've got A and B, and if I were to just, almost like we were using our tail to tail to find our resultant vector, but instead of finding the resultant vector, I just end up with this shape, right? I end up with this parallelogram shape. And the area of that parallelogram shape is the magnitude of A cross B. Okay, so in order to find the area of the parallelogram with adjacent sides, and the adjacent sides are our vectors u and v, we just need to find the magnitude of u cross v. So first let's go ahead and find out what u cross v is. So we'll take our matrix, find the determinant of this matrix. That'll look something like this. And we'll find that our u cross v is negative 11i minus 18j minus 10k. So now we just need to take the magnitude of this. We'll go ahead and plug this in, plug in our values. So I've got 11 squared plus 18 squared plus 10 squared. And we get about 23.3 units squared for our area. All right, last example here, we're going to find the volume of a parallelepiped. Okay, our adjacent sides. We have t, like I said, t would often be what you would see here for what you will substitute in for your unit vectors. And then we have vectors u and v, okay? And they're given to us as linear combinations. That's totally fine. We can still take our components and plug them in here to our matrix. So we just have our matrix here. We're going to plug in all of our components for t, u, and v. Keep in mind, I don't have any component in the I direction for t, so that's just going to be a 0 there. And then I need to take the determinant of this 3 by 3, okay, which looks something like this. And once we simplify that, we're going to get 86, okay? So again, this is going to give us some scalar value because I don't have my unit vectors anymore. I just have these components of vector t. Okay, so when I take the determinant of this, I'm going to get a scalar value, and that scalar value will represent the volume of my parallelepiped. Okay, and in this case, it'll be 86 units. That should be units cubed. Okay, so that is all that I have for you guys for this lesson. Good luck with your practice.